In this session, we will cover different techniques or methods which are already built into the optimization module for problems without constraints and different kinds of constraints and different different methods that are in scipy.optimize. Okay. So far, in the last few sessions, we've been looking at an optimization problem. Basically, the idea is that you've got a squared error. It could be any kind of a functional that has, you want to minimize the value of the functional, you want to minimize the value of that functional by manipulating the input to the functional. Okay. And so we looked at one technique, basically gradient descent, for doing that. And we will now we'll see what we can do just by asking scipy to do all the hard work for us. The optimization module in scipy should do the work for us. Okay. So let's start with the simplest problem we can think of. Is a problem where there's a single input, or there's a single real number coming into a function. The function is spitting out a real number, and we want to know for what value is that function, let's call it f, minimized. Okay. So for this problem, what we're going to do is the problem is f of x is equal to exponential of x minus 1 squared. So the x minus 1 is squared. And you can see right away that the minimum should occur at x is equal to 1. Right? So I don't really need a computer to do this for me. But let's see what methods can be used to do this. Now, scipy.optimize has different minimization methods, but this is a scalar problem. Okay, so this has a single real input and the function is a single real output. Okay, so that's called a scalar problem, and it has a particular method for dealing with scalar problems. Okay, so you don't want to use scipy.optimize.minimize here. It would be better to use the specific method for minimization, minimize.scalar. Okay, so this is the way you do it. You import numpy, let's say, as np. From scipy, what we want is the optimize, the various methods for optimizing. So from scipy, we import optimize. We need to define the function that we want to minimize, whose value we want to minimize. So let's call that f. So define this function of f. Now, that function was exponential of x minus 1 squared. It might need to know where that exponential function lives, right? But numpy has an exponential function defined in it. So I'm going to use that one. So the result is equal to np dot exponential of x minus 1 squared, and you're going to return the result. So now you've defined the function whose value you want to minimize, and you know that it's a scalar function. Okay, so now you imported optimize from scipy. So what you can do is you can say optimize dot, there's a method called minimize for scalar function. So minimize sub scalar of, and you have to feed it which function you want to minimize, and that function we called f. And you put the result, whatever the output of this action is, put it into result. Okay, and then you run it. Okay, is that okay so far?
Yes, sir.
All right, so now minimize subscalar is actually going to report a lot of things to you. So one thing you might want to know is, did it run successfully? So it's got an attribute called success. So if you ask it to print result.success, it gives you a true. All right. So let's say that you have a loop, let's say, and you're calling this minimize subscalar repeatedly. You might not want it to be spitting out everything that would be contained in result. You might just want to know until you're done. You may just want to know that it's it's executing successfully. So you're checking to see perhaps that it's successfully done its job, and then you can go on to the rest of the loop, let's say. Okay, so you can just have it report the success. Okay, it's got another attribute called x. So result.x is the minimum that it found. So I can ask it, I can say something is equal to result.x, and then I can ask it to print that. I know in this particular case, it's a simple function. I know that the minimum should occur at x is equal to 1. So I'll ask for the difference between its approximate result and 1. And basically, it says that the result was 1. The minimum occur, which means the minimum occurs at 1. Result.x is where the minimum occurs. And the difference between that and what I know the minimum should be is 0. Now, we could ask it for some more information. And let's see, let's go back a bit. Sorry. Where was I? Yeah. So if I say there was this method that I had, and what was it called? It was called minimize subscalar. And I asked it that, right? So now it's given me some information about it. And it's told me that it brings in, it requires fun, which is the function. You could also give it some bounds. The default is not to give it any bounds. You could give it some arguments right? You could give it some arguments. It defaults to a method called Brent, but we can set other options for it. We can set a tolerance for the method, whichever method we're using. And we can set some options. Right now, they're by default, they're set equal to none. Okay. So there's a method called bounded that you can call. And then bounds can be given as 2 items. And you're looking for the minimum between those two things, those 2 bounds. Okay. And you can call different methods. One of the methods is Brent, one is bounded, one is golden. You can get information about those also if you want. And you can customize the method that you're going to use. Okay. And the options would be a dictionary. I'll talk about dictionaries in a moment. Okay, so let me talk about dictionaries in a moment. Okay. So that's how you get some information about that. Now, so here's an example using some of these options. So let's say the result, you run minimize subscalar using the function is this f that we talked about. I'll use the method bounded, and I will set the bounds to be between 2 and 3. Okay. So that's not where the global minimum of this function is. Okay. But that's where I want to, maybe there's some reason in my particular application that x has to lie between 2 and 3. And so then I restrict it to looking within those bounds. And now when I ask result.x, the estimated where the minimum is, it's estimating the minimum to be occurring very close to 2, which kind of makes sense. Is that okay? You can also do a bounded search. Okay. We've already covered gradient descent, so I won't do that. Okay, conjugate gradient. If you've done a bit of linear algebra, you may already have heard about this. And with gradient descent, you're just looking in the gradient direction or minus the gradient direction for the minimum. With conjugate gradient descent, what happens is that you look in the gradient direction and you also look in other directions. And for some problems, that might turn out to be more efficient. Okay, so that's a very fuzzy description of the conjugate gradient method. We will maybe discuss that a bit later. But anyways, now let's say that I've graduated from doing only scalar problems. Now I want to do multivariable optimization. Okay, so I don't use minimize subscalar. I will use minimize. Okay, and minimize has it has various options, and one of them is the conjugate gradient method. You can use the conjugate gradient method if you want. And it's there, if you want to use the conjugate gradient method, you set that as capital CG as the method to be used. Okay, so now let's say that we have this function. It maps, you feed it 2 real values and it gives you 1 real value back. So you have f of xy is equal to 1 minus x squared plus y minus x squared quantity squared. Okay, so I'm going to look for the minimum of that function. So like the scalar case, in the multivariable case also, you need to define the function that is to be minimized. So I define the function, and that's, I'm going to give it an array, let's say, or a list of numbers. And x of 0 I'm thinking of as x, and x1 I'm thinking of as y. Okay, so I feed it in 2 numbers as an array or a list, and that's 1 minus x0 squared plus x of 1 minus x0 squared, and then all squared. Okay, so I've defined the function that is to be minimized. Okay, now I'm not going to use minimize subscalar because this is not a scalar problem. I'm feeding it in an array or a list. Okay, not just a single real number. Okay, so I can't use minimize subscalar for this. I will use optimize.minimize. Okay, so I'm going to use optimize.minimize with these options. The function which is to be minimized is this function I'm calling f. X0 means the initial guess. So what I could do is I could use a plotting, or I could use Wolfram Alpha or something, and I look at the graph or the surface that it produces, and I say, yeah, I think the minimum is somewhere near 0, 0. So x0 here, the option x0 is set equal to 0, 0, which means start with x0 is equal to 0 and x1 is equal. So x0 equals 0 and x1 is equal to 0. Now I have a bunch of options that I can use. One of these options is a bunch of methods that could be used. I'm allowed to choose between them. It probably has a default if you don't choose, okay? But if I specify it, this time, let's specify that this is the conjugate gradient method. And the way to specify that is to say that method is equal to capital CG. Okay. And all the workings, everything that it reports should be shoved into this thing that I'm calling result. Okay. Well, I run that. I say result.message. The message it gives me is that the optimization terminated successfully. Result.success, yeah, it says that it's true. So once again, you may not want, if this is happening in a loop, if this is happening continuously, 1,000 times in your program, you don't want it reporting everything to you on the screen. So maybe you just want a check or a flag to say if, the result, if there's a success, then just keep going through the loop. And if there isn't, then you need to break the loop and give me the message or something like that. Okay. What estimate does it give? It gives you something. It says that my estimated, the minimum I estimate as occurring at x is equal to, x0 is equal to this number, and x1 is equal to that number. These are very close to 1, 1. And if we look over here, this function cannot be negative, right? Because I'm squaring things. The least value that it could have would be 0. And one of the places where it would be 0 would be if you set x is equal to 1 and y is equal to 1, you would see that this is equal to, this would give you 0. So we suspect that the minimum actually occurs at x equals 1 and y equals 1. And this is giving me results that are very close to x0 equals 1 and x1 equals 1. Okay. The least value that this function can have is 0. Result.fun gives me the value of the function near the estimated critical point. Sorry, at the estimated critical point. And it's given me something very close to 0. So that's the estimated minimum of the function. Okay. Now it's also returns the Jacobian. Unfortunately, some people use the Jacobian for what I call the Jacobian. Some people use the terminology Jacobian for what I call the gradient. I think what's happening here is they're actually reporting the gradient. Okay. And right, from calculus 2, that if you've got some function of x and y, at the minimum, you expect that the partial with respect to x should be equal to 0 and the partial with respect to y should be equal to 0. Or perhaps the partial shouldn't exist. Okay. So are the partial with respect to x0 is very close to 0 and the partial with respect to x1 is very close to 0. Okay. We haven't actually specified the gradient here. So what it's doing is it's estimating the gradient numerically. Okay. All right. So everything's consistent with finding a minimum or being very close to a minimum. Okay, for a multivariable function, how do we check that we've actually got a minimum or a maximum? From calculus 2? Okay, from calculus 1, we have a function f of x, and let's say it's differentiable, and I can actually calculate. It's nice enough that I can calculate first derivatives and second derivatives, right?
We look at the sign of derivative.
Yeah, so you say it's a critical point if the first derivative is equal to 0, and then you check whether the second derivative is greater than 0 or less than 0, and it tells you whether you have a max or a local max or a local min. And then there's an equivalent idea if you have a function of two variables, f of x, y. And then there are tests that involve the second derivatives, and they can tell you whether that test can tell you whether you have a max, a min, or a saddle point, right? So to actually check that we have a minimum here, using calculus. Now, from the form of the function, we know that 0 is the minimum, right? But in general, for a function, what we would want to do is we would want to calculate the Hessian, which is a matrix of the second derivatives, and then do the derivative of the Hessian, whether that's greater than 0 or less than 0. That would give us some information. Okay. So there you have the gradient. The values of the gradient are almost equal to 0, as they should be. Okay, so like I said, where exactly is this gradient? It's been estimating the gradient numerically as it did this problem. Okay, so Jack stands for Jacobian, which actually should have been called gradient. It's been estimating that gradient numerically. Okay, but let's go back to the function. This is a fairly simple function. And I could calculate the partial derivative of f with respect to x and the partial derivative of f with respect to y. I could calculate that very easily. And even if it was a bit more complicated, I could just give it to Maple or Wolfram Alpha or something and have that calculated for me, right? So over here, I've calculated the gradient. Okay, so the gradient function, if you give me an f, I can calculate the gradient. Remember, the gradient is the partial is the vector whose entries are the derivative of f with respect to x and the derivative of f with respect to y. I'm thinking of x0 as x and x1 as y. And so this is what the gradient would be. The result is an array, right? So this is what the gradient would be. This function df calculates the gradient at a given x0, x1. Okay, and it returns that result as an array. Okay, so now I can optimize. Okay, so let's go back here and let's see what the Okay. All right. So over here, if we go back, we did not give this function, we did not give this method minimize a gradient. We let it calculate the gradient itself or estimate the gradient itself. Here, I'm going to estimate, I'm going to feed it this gradient. So I say, as I did before, the function to be minimized is f. Start at 0, 0. The method is the conjugate gradient method, capital CG. And now I'm going to tell you the Jacobian, well, actually the gradient is equal, can be calculated using this function df. Right? And everything that you calculate, stick it into the result. Now let's print the result. Okay, so the message is that it optimated the optimization terminated. The gradient at the estimated minimum critical point is almost equal to 0, 0. The function value is very close to 0, right? What did we have before? So here the result of the function was 6.86 times 10 to the minus 12. And here it's like 9 to, so it's almost the same. Now, here's a couple of more things that it can report to you. NFEV means the number of function evaluations. So the function was evaluated 34 times. There were 17 total iterations. There were 34 Jacobian evaluations. It managed successfully. And the estimated critical point is x0 equals 1 point something and x1 is equal to 1 point something. Okay. So like I said, in this case, the gradient was easy enough for me to calculate, so I did. If it was a little bit more complicated, I could either use something like Wolfram Alpha, Maple, right, Mathematica, or I could use the symbolic package for Python. It's called SymPy. Okay. And, you know, if you can calculate the gradient, I think you should, right? All right, now the Newton method. So Newton methods are somewhat more expensive in terms of function evaluations typically than than other methods. On the other hand, they have very quick convergence if you are close enough to the point that you're interested in. And one thing you might want to do is actually use two methods. Use a simpler method at the beginning, and then switch to a Newton method after some time, right? But anyways, let's just say we just want to use the Newton method. Okay, again, I can write my own Newton method, or we should all be capable of writing our own Newton method. But the ones in this module are written so nicely, they're likely optimized, and I can use them for all kinds of functions, right? So if we want to do that, so we make a change, right? Remember, Newton's method in one dimension, it involves the derivative. So Newton method in multiple dimensions will involve the gradient, okay? So I'm going to, the same function f, the same starting point 0, 0. I'm going to change my method to Newton dash conjugate gradient. And I'm going to tell it where to find the way to calculate the gradient function is in this function df. Okay, now I print the result. So now look at what happened. This is like 10 to the minus 10 times 10 to the minus 12. This function is somewhat closer to 0. We're talking about 9 times 10 to the minus 18. The Jacobian also seems to be a little bit closer to 0. Well, maybe not. Now look at the number of function evaluations. NFEV was 8. This was 34. So it got there much earlier. The number of iterations was 17. This time the number of iterations was only 6. NHEV means the number of Hessians. So the Hessian is a matrix which has the second derivatives in it. So it didn't bother to call the Hessian. And it converged right to pretty well to the point that I wanted. Okay. All right, so is that okay? All right.
Yes, sir.
Now, okay, so I've referred to the Hessian a couple of times. Let me remind you what the Hessian is from Calculus 2, okay? So I have a function. The Hessian of that function, well, I mean, I'm just showing it for two variables, but it has a multivariable extension. But just for 2 variables, the Hessian looks like this. The rows look like fx, right? So these are the partial derivatives. So that's d2f by dx squared, that's df by dx, and then d by dy. Then the derivative with respect to y, and then take the derivative with respect to x, and then the double derivative, partial derivative with respect to y. Okay? For nice functions, typically that we're concerned with, it doesn't matter whether you take the derivative with respect to x and then with respect to y in that order, or whether you take it with respect to y and then with respect to x. They should both be the same for nicely behaved functions. All right, so in particular, if we go back to the original function up here, we take this function f of x, y, and we calculate its second derivatives with respect to x, with respect to y, and the partial mixed derivatives, then and we stick those into the Hessian, then that's what the Hessian matrix looks like. All right. So in this case, it's very simple. I can do it by hand. And if it's kind of tedious, or if you've got 4 variables in the system, for example, it gets tedious to do. So no problem, give it to Wolfram Alpha or give it to Maple or Mathematica, and they will spit out the Hessian for you. Or, like I said, use SciPy. Okay. So anyway, somehow I calculate the Hessian. That's the Hessian, right? Okay. And I have a matrix. I take an X, and then what it will do is it will construct this array, this 2 by 2 array for me to represent the Hessian in this function. Okay, so now I can optimize, and I'm giving it everything that it can use. The function, the starting points, I'm going to use Newton conjugate gradient. The gradient is defined in df, and the Hessian is defined in this function that I've called Hessian. And I run it now if I print the result. Okay, so the number of function evaluations was 8 in both cases. This time it called the Hessian 6 times. Before it didn't, right? The number of iterations is 6 again. Number of Jacobian gradient evaluations is 8. And it gives me something very close to 1, 1. Okay. So, well, I'm using the math that I learned before, or that I had to remind myself of from the multivariable calculus course, Cal 2, right? The Jacobian, the Hessian. and but then all the hard work is being done by this minimize method. Okay, and the method, as I said, the method can call various methods as you like, and with many options. And before you use it, please read about the method properly. Okay. So, any questions so far? All right.
Professor, when we're declaring the Hessian, we should do f with respect f with partial xx, f with partial xy, and then yx yy, right? In when we put when we import the array.
I'm sorry, there's a bit of ambient noise here. I'm just going to step away and turn off the fan here so that I can hear you a bit better. Okay, please ask again.
So, Professor, when we're declaring the Hessian, right, we do xx, xy, yx, and yy, and just like one array, right? We don't have to sort of split that up, right?
No, yeah, you just do it in one array. Okay. All right. So now all the things that we did, we actually did one example with a constraint. We said, I want you to look for the minimum within a certain interval for the scalar case. All right, so let's say, again, now that we want to do some minimization, and the quantity is subject to a constraint. So it might be something like, I want you to minimize this, and for some, my real world application is such that x has to be greater than or equal to 2, for example. Or I might have something like, here's the minimization problem. I'm particularly interested in the case where x of 3 is equal to 0. So that's an equality constraint. So we want to be able to do minimizations subject to a constraint. Okay. So sometimes a common case would be a box constraint. Okay. So I want values to lie. Supposing that I want to do the same problem, the same function, and I want to tell it, as we did before, I want to give bounds. So now this time I want to give bounds on, there are two inputs, x and y, or x0 and x1. So I want to give bounds on what x0 and x1 can be. So I can set the bounds equal, the bound for x0 is this, minus 1 point, sorry, minus 1.5 to 1.5. And the bound for x2 is similarly minus 1.5 to positive 1.5. So there's a method called LBFGS-B, okay? L stands for limited memory. And what that means is I'm going to estimate the Hessian from previous gradients. Okay, I'm not going to specifically calculate the Hessian. Because you can imagine if you've got say 100 inputs, then the Hessian is a matrix, or you can think of it as a matrix with 10,000 entries, right? So maybe we're better off estimating the Hessian rather than calculating it each time. Okay, and the dash B means box. So you're specifying a box within which you've given the range for all of the various variables, and within that box might be an n-dimensional box actually. Within that n-dimensional box, that's where you can look. Okay, so the way you would do it is you'd say, all right, I want you to minimize that function which I've called f. I want you to start with initial guess 0, 0. The method to be used is this limited BFGS dash box. The gradient is to be found, can be calculated from DF, and the bounds I'm given on the first variable is minus 1.5 to 1.5. And on the bounds on the second variable are from minus 1.5 to 1.5. Right. And if I print the result, well, it gives me a message that the norm of the projected gradient is less than the tolerance for the projected gradient. The function value is very close to 0, and the estimated critical point is very close to 1, 1. Okay, so that's one way. If your constraints are box constraints, then it's got a method. Then it's got a method that's where you can easily define those bounds. You can easily define your box within which you're going to look for the critical point. Okay. What if it's a little bit different? So let's say I've got this function, same function as I have before, and now instead of looking within a box, I'm going to look on a line. So I'm going to say there's a line, and the line is defined by y is equal to 2x. So I want you to find the minimum value of this function subject to the condition, what is the minimum value on that line? Y is equal to 2x. So the actual minimum for the entire function without any constraints is different, right? This is a different problem. Now, the proper way to do this problem would be to set y equal to 2x in the function, and then we would reduce the dimension of the problem, and it would be easy to solve, right? But you know, these are prototypical problems to show how you go about doing them using this minimize with constraints. So let's say I don't know how to do it the right way, so I'm gonna let the computer do it. So now think of the constraint this way. I could write the constraint as 2x minus y is equal to 0. Or I could write the constraint as y minus 2x is equal to 0. Which, let's say we're going to use 2x minus y is equal to 0. So I need to define that constraint. So I need the original function has to be defined as a function. The constraint has to be defined as a function. And this is an equality constraint. There are other types of constraints that can be used. So I need to be able to tell, as some parameter, I need to be able to tell minimize that I'm using an inequality constraint here instead of some other kind of constraint. Okay, so that information is provided in a dictionary. And I haven't discussed dictionaries yet. Some of you will already know what a dictionary is, but those who don't, for our purposes, it's something that's very simple. Okay, so we've discussed sequences before. So we have lists, we had NumPy arrays, we had range. So these provide a sequence of things. And these are indexed by an integer, right? X of 0, X of 1, X of 2, and so on. X of 1, 3, or something, right? So they're indexed by integers. Now, in dictionaries, what you have are a sequence of key value pairs. It's easiest just to give an example. Okay, so let's say I'm setting up a very simple French to English dictionary. So here, and dictionaries are set up with curly brackets. Okay, So animals equal, and then in curly brackets, I've got a bunch of key value pairs. So the key is cheval, the value is horse. The key is chat, the value is cat. The key is chien, the value is dog. Okay, so what is that? That's a very simple French to English dictionary for the names of animals in the two languages. Okay, so if I print it, it just gives me these key value pairs. And now the indices here are the keys, cheval, chat, and chien. So if I ask it to print animals of cheval, that is, tell me what cheval means in English, basically, it will say that I ask it for I index this by the key, and it gives me the value, which is horse. Okay, I can change, this is animals of cheval, I can change that to monkey. And now if I print animals, it says that the meaning of cheval is monkey, which is wrong. Okay, but I can make small changes like that. Okay, I can change values in a dictionary, but I can't change the keys in a dictionary. Okay, so back to our example, this is how you'd do it. I have a function for my equality constraint. You can call the function whatever you want. So I just called it EQ subconstraint to stand for equality constraint. And if you feed it in x, what should happen is that twice x0 minus x1, that's the result. And that should be equal to 0. So now there's only, what you do is you give it a dictionary, and for each constraint, you have to specify, is this an equality constraint, EQ, or is this something else? And that equality constraint is being given to me by which function? In this case, the function is EQ subconstraint. So I give it the constraint dictionary, and if I had another equality constraint, for example, I would then have to write comma after these two pairs. I'd have to write type colon EQ comma function colon, and then I would have to give it the name of the second function, which defines the second equality constraint. Okay, so now I'm going to minimize that same function using this constraint that twice x minus y should equal 0. Okay, or that y is equal to 2x. So optimize.minimize, the function is this function f. The initial guess is 0, 0. I should probably start off on a guess, which is actually on the line. And in this case, it is, right? And the constraints, tell it which dictionary holds the constraints, specifies the type of constraints. And the dictionary which is specifying the types of constraints is this one where we call const subdict. Okay, so now we run that and we ask, all right, so now the function value is close to 0.75. The Jacobian isn't anywhere near 0. Okay. There were 18 function evaluations, 6 iterations, 6 gradient evaluations, and this is the point that it found. Okay. All right. So if you had more constraints, then you would you'd have a longer dictionary, and you'd have to have more functions to define those constraints. So it can also handle inequality constraints. For example, if some value has to be bigger than another value, x minus y has to be greater than 0 or something, you can also specify constraints like that. Okay, so you might want to set a problem for yourself, find the point that's closest to the origin on the plane x that's defined by x plus y plus z is equal to 3, for example. Try that and see if you can get that to work using minimize and using an equality constraint. Okay, so are there any questions? Okay, if not, then Riaz will start taking lectures again from Wednesday. Okay, so I'll catch you later.
Professor, could we get like sort of some practice sets or something so that we could sort of get a better handle of this before we get assignments?
Well, I'm going to give you a take-home midterm next week, right? So
Yeah, something before that to sort of practice on our own time though.
okay, so practice using minimize.
Yeah, minimize and like any other sort of optimization that we might be doing in the midterm.
Okay. All right, I'll send you. I'll try and work out a practice set over the weekend. Okay.
Thank you.
Okay. Bye.